All right, guys, today we're talking about the quadratic formula and applications of the quadratic formula. We'll also be talking about something called the determinant, which is part of our quadratic formula. Well, it'd be kind of senseless just to give you the formula. You've seen it before, but now we know the steps to derive the quadratic formula. And in fact, we use the steps for completing the square. So we're going to start by deriving the quadratic formula using completing the square. If you really don't care about how to derive the quadratic formula, you could skip ahead to using the quadratic formula, and of course what the formula is towards the end of this slide. But I don't know, it's pretty fun to derive things, so let's try that. Okay, so let's start with the generic quadratic in standard form, ax squared plus bx plus c. So following our steps for completing the square, right over here, the first thing we do is divide all terms by a if necessary. Well, in this case, we assume a won't always be 1, so that it may be necessary. So the first thing we do is divide everything on both sides by a. Okay, so our first term, the a's cancel out. We're going to have x squared plus b over a times x plus c over a. Okay, so we do end up with a couple fractions that have a underneath. That's fine. Our second step in the quadratic formula over here is to move the constant c to the other side. So this would be our constant, this fraction. So we're going to subtract that over. And it should look like negative c over a over here. So we're subtracting it from both sides. I'm just going to not write the actual subtraction step. Save some space here. Okay, so now we have this. And remember, we set up plus blank in its place on each side. Okay, next, to actually complete the square, remember we needed to find half of b, or 1/2 times b, quantity squared. And we said to use this one specifically if b was a fraction. And since we do have a fraction here, we're going to multiply it by 1/2 and square it. So our side work here will be to take b over a times 1/2 and square it. So top times top, bottom times bottom gives me b over 2a squared, which will give me b times b is b squared, and 2a times 2a is 4a squared. So we need to actually add b squared over 4a squared to both sides. B squared over 4a squared. Okay, so we're on our way. Now remember, we used kind of a hack to help us factor things that were perfect squares, that we used half of b before it was squared, right? Half of b, so this b over 2a part, is what our perfect square on the left will factor as. So this left side, this perfect square we created, those are some ugly parentheses, is going to be x plus, and in this case, b over 2a. This is the perfect square that we've created on this side. Remember, again, it's the half of b value before it's squared. Now, on this side, we have some fractions that we want to combine, and in order to add fractions, we need a common denominator. So because this denominator is 4 times a, and this denominator over here has just one a, to get them to be the same, we're going to need to multiply the fraction on the left, top and bottom, by 4a. So I multiply this by 4a and this by 4a. We'll have the same denominator, 4a squared. Now, just to change the order to make this look like quadratic formula, I'm also going to write the b squared minus 4ac, or sorry, not b squared minus 4ac, I'm getting ahead of myself. B squared over 4a squared, this, I'm just writing it first, okay? And then we're going to write this new one next to it. So we're going to write minus 4a times c, so I'm just keeping that alphabetical, over our common denominator, which would now be 4a squared, right? 4a times 4, 4a squared. And now that they have the same denominator, we can add or subtract the numerators, right? And keep the denominator, just like when we're working with fractions. So we can write this as b squared minus 4ac all over 4a squared. Okay. equals our x plus b over 2a squared. You might recognize some of this. This is starting to look a little familiar, hopefully. And hopefully that you understand the reason why I changed the order there to make it match this form. Okay, next we knew when we're using completing the square, we would take the square root of both sides after we've created our perfect square. So we're going to square root both sides. Don't forget to put plus or minus. So we're going to have a plus or minus on the left here, or sorry, on the right. And remember properties of radicals, we said we can separate the top and bottom as individual radicals. So square root of 4a squared. And over here, of course, the square root and square are canceling each other out, and we get x plus b over 2a. Okay, well, the reason we want to separate those radicals on the right-hand side is the bottom is actually a perfect square. The value times itself twice that gets me 4a squared is 2a. So our denominator on the right is 2a. So I have this plus or minus. Now I can't simplify the top because there's subtraction in there. And there's our plus or minus, which I guess I could have put in the front there. It's all right, we'll fix this plus or minus. Sorry, b squared minus 4ac. And then our last step here is to move the b over 2a to the other side, right? We want to get x by itself. So I would need to subtract this over and keep it in front of the plus or minus. So if I subtract b over 2a, and we put that in front of the plus or minus, and oh, I forgot my a over here. Sorry, the bottom was 2a, right? So apologies for my mistake. And now we see that these actually have the same denominator, right? They're both over 2a, so we can write this as one big fraction if we like. Negative b, or opposite of b, plus or minus the square root of b squared minus 4ac, all over 2a. And there you go. This is our quadratic formula. You've definitely seen this before. And this is basically just a way you can get your two solutions for any quadratic using completing the square, but instead of going through all that fraction work, we can just plug numbers in our formula and get our answer right away. Okay, but one thing that you need to be careful of, this condition at the beginning needs to be true. My quadratic has to equal 0 before I plug in values of a, b, and c and solve using that formula. So make sure you're satisfying that condition first. So let's try some examples where we're asked to solve a quadratic using the quadratic formula. And so I've placed it over here for reference as we plug in our values. So the first thing you want to do is make sure your equation is set equal to 0. Remember, that's the condition where we derive the formula. And then I want to identify the values of a, b, and c. Okay, so my a value here is a positive 1 in front of x squared, b is the positive 6 in front of x, and c is negative 40. So plugging into our formula, x is equal to the opposite of b, so negative 6, plus or minus the square root of b squared minus 4 times a, which is 1 times c, which is 40. So it's minus 4 times a times c, all over 2 times a. Okay, now I need to make sure that I simplify inside of this radical first. So we always do that part first with our quadratic formula. So the first thing we're going to do is our exponent inside of there. So the 6 squared is 36. Minus, and now our next step would be to do the multiplication of all three of these terms over here. So since we've already done our exponents, you can kind of get away with doing them in the same step here without really violating our order of operations. So we'll go ahead and do that. Negative 4 times 1 is negative 4, but negative 4 times negative 40 is actually going to be positive, so we're going to write plus 160. So a pretty big value there. But because we had a negative 4, a 1, and a negative 40, together that ended up giving us a positive value back. And we can go ahead and simplify the denominator at any point. 2 times 1 is 2. Okay, Okay, now if we add the values up there in our radical, 36 and 160 is 196 all over 2. And now I have this large value in my radical that I need to simplify. So I need to simplify the square root of 196. You may recognize that, you may not. So let's say I do my factor tree. That would be 2 and 98. That's 2 times 49. That's 7 times 7. And we end up, everything gets a pair. We have a pair of 7s and a pair of 2s. So both a 2 and a 7 come out of my radical. And there's nothing left inside. So actually what that means is 196 was a perfect square. We end up getting exactly 14. 14 is the square root of 96. Okay, so we have -6 plus or minus 14 all over 2. We ended up getting a nice exact value. And when you do get an exact value over here, we can actually go ahead and calculate this out and keep our answers as exact as possible. So we have two cases. We have -6 plus 14 over 2. And then we also have -6 minus 14 over 2. So let's find our two solutions here. -6 plus 14 is 8, and 8 over 2 is 4. There's one of my solutions. -6 and -14 make -20 over 2, which is -10. So we end up getting two solutions here. X is 4 and -10. Now, if you do use quadratic formula and you get a perfect square under your radical like we ended up here with 196, what that really means is that you could have solved this through factoring and probably saved yourself a lot of time. In fact, if you came back up here and thought about this as far as factoring, right? I know my factors would have opposite signs because they multiply to -40. And the factors of 40 that subtract to 6 are +10 and -4. And if you set each of those equal to 0, we get -10 and +4. And that would have been tons faster. Okay, and the reason I did this as the first example is I wanted to show you guys that yes, quadratic formula does always solve quadratics, but sometimes it's like one of the slowest possible methods. Factoring is much faster when we can use it. Okay, so let's try this next one. A is 1, B is -8, and C is 10. And again, it is set equal to 0, so we can go plug in. X is equal to the opposite of B, so +8, plus or minus the square root of B squared minus 4 times A times C. And you might notice that I plugged in both times I plugged in B squared, I used parentheses. That's because if you plug in a calculator and you plug in this, it will give you the correct answer of +64, which is what we want. If you type in this without the parentheses, it will give you back -64, because your calculator thinks you want the opposite of 8 squared and not the number -8 times itself twice. So just be careful. If you are plugging in with a calculator, make sure you use parentheses there. Okay, back to our formula, that's all over 2 times A. Okay, so simplifying under the radical there, 8 squared or -8 squared is 64. And we can go ahead and multiply these three numbers together. -4 times 1 is -4, times 10 is -40. Go ahead and simplify the denominator as well. 2 times 1 is 2. Now we can subtract inside the radical. 64 minus 40 is 24, all over 2. And now I want to simplify my radical. So the square root of 24, well, that's 4 times 6. That's 2 times 3, 2 times 2. So we're going to get a pair of 2. So a 2 will come out of my radical. And this 2 and 3 left over get multiplied back inside. 2 times the square root of 6 is our simplified radical. Okay, now this next part, it's important to think back where we saw the quadratic formula as kind of two fractions like this. Right, before we wrote it as one big fraction when we derived it. So if all three values outside the radical, and if the radical doesn't simplify, then you won't simplify this statement. Okay, but if all three values outside the radical here, 8, the 2 that came out in this 2, if those 3 all have a common factor, you can reduce. So if I divide those 3 values, and it's only those 3, don't change what's inside the radical, we would get 4 plus or minus 1 root 6 all over 1, in which case we don't even need a fraction anymore. So in fact, my 2 solutions, and I would have to either go to a decimal or we can leave them here, is 4 plus the square root of 6 and 4 minus the square root of 6. Those are the 2 decimal values where my graph crosses the x-axis. Okay, now even this type of answer, if I get something that has plus or minus and a radical, but there's no fraction underneath, in other words, this fraction simplified to no longer needing to be a fraction, it actually tells me completing the square was a little bit faster for this problem than quadratic formula, but I know most of you will probably go quadratic formula. Okay, let's try a few more examples. I might do these very quickly here, so I will do one of them and then I'll leave the other for you to try out, because I don't want to make this video crazy long and we still have a few things left to get to. So here A is 3, B is 5, and C is 10, all nice positive values. My quadratic was set equal to 0. So x is equal to the opposite of b plus or minus the square root of b squared minus 4ac, need to extend my radical there, all over 2 times a. This time a was not 1, it's a value of 3. All right, so 5 squared is 25. Negative 4 times 3 is negative 12. Times 10 is negative 120. And simplifying the bottom, 2 times 3 is 6. So negative 5 plus or minus 25 minus 120 is negative 95. All over 6. Now I need to simplify my radical. And I notice, hey, I have a negative number in my square root. Hopefully you know that means that an I is going to come out here. So negative 95 will give me the square root of negative 1 times 95, right, which is I times the square root of 95. And then we want to try to simplify the square root of 95. Well, 5 definitely goes in there. It goes into 9 once with 4 left over, and it goes into 45 9 times. So 5 and 19, those are both prime, and there's no pairs. So in fact, the square root of 95 does not simplify, but we can and need to take that I out of our radical. So our final answer here, because since we didn't get to take a number out of our radical, only I, whoops, sorry, not 6, we won't be able to reduce the overall fraction. So we end up getting negative 5 plus or minus I root 95 all over 6. Now, if you really wanted to think about this as a complex number, the real part would be the negative 5/6, and the imaginary part would be the I root 95 sixths. So that's how you could separate it to be looking like a complex number. And what this means, because we got 2 imaginary answers, is that my graph never crosses the x-axis. In fact, I know this graph opens up because a is positive 3. So its vertex must be above the x-axis, and it just never goes low enough to cross it. So we get imaginary solutions. So graphically, that's what an imaginary means. Okay, try example 4 out. Pause the video and check and see if you got the same answer. All right, here is our solution. You came up with negative 1 and negative 7/4. Excellent job. The radical value you should have gotten was 121, which is 11 squared. So nice perfect square. Separating into your plus and minus case down at the bottom should result in your 2 final solutions. So yes, one of them did become a fraction here. Just make sure that you simplify that as far as possible in your solutions. Once again, if your radical ends up being a perfect square, that meant that your quadratic was factorable. So you could have also solved this quadratic by moving everything to the other side where x squared is positive and factoring. Okay, our next important part about the quadratic formula is the part under the radical. The b squared minus 4ac is called the discriminant. So it's the part under the radical in the quadratic formula. Okay, and what we can use the discriminant for by itself is to quickly determine the number of real or imaginary solutions, imaginary/complex. So think about this, if that number under my radical is positive, like 30, right? We have some number out here, plus or minus the square root of 30 over some number, doesn't really matter. But if this is positive, well, it's an irrational, it's an ugly number, but it gives me something that's real, right? We're going to get a real and another real. We end up getting two real solutions. So that's what this says. If the part under the radical, the b squared minus 4ac, is any positive number after you do that calculation, you will get two real solutions. Okay, and what that means, if you're getting two real solutions to your quadratic, if you graphed it, it will cross the x-axis twice. Okay. If, however, you end up getting under your radical here exactly 0, so let's imagine that we instead got exactly 0 under our radical. Well, when we go to take the square root, plus or minus 0 is a pretty small value. Uh-oh, I don't know what's happening. Here we go. Sorry. We do plus or minus 0. Well, the square root of 0 is 0. And if I add 0 or subtract 0 from this, I'm going to get the same answer twice. So what that means is we end up getting a repeated solution. Like you might get -3 and -3, right? The same value twice from your quadratic. So if that's true, that means we're going to say that that repeated solution technically only counts as one unique, so one real solution. And graphically, the only way that's possible is if like the vertex of your graph is just touching the x-axis, if this is the x-axis here. So that's what it means if you get a discriminant of 0. The vertex is right on the x-axis. It's the only way for it to cross once. Okay, our last scenario here is what if the number under my radical is negative? So -10, for instance. So some number plus or minus this over some number. Well, if this is negative, we know we're getting an I in our answer. And because it's plus or minus, there are two solutions. So if we get a negative value from our discriminant, if it's less than 0, then we get two imaginary or complex solution. And what that means graphically is maybe I've got my parabola and it goes up and never crosses the x-axis, or maybe my parabola was below it and it's opening downwards, but it will never cross. It has no real solutions, but it does have two imaginary or complex solutions. So let's quickly try these. We're just doing the b squared minus 4ac to answer this question. Find the number and types of solutions for each using the discriminant. So all again we need to do is identify a, b, and c, and do our discriminant, the b squared minus 4ac. So 5 squared minus 4 times a times c. So b squared minus 4ac. This is 25, and we know we can go ahead and multiply these together, which gives us -40. And I end up with -15. So keep in mind, this is the part that would have been under the radical, right? So we would say this is the value of my discriminant, and then what does it mean? It means we're going to get two imaginary or complex solutions. It also tells me that my graph never crosses the x-axis. That's why we're getting imaginary solutions. So remember, when the discriminant is less than 0, if it's any negative number, we get two imaginaries. Okay, let's try this next one. A is 3, B is 6, and C is also 3. So b squared, 6 squared, minus 4 times a times c. This gives me 36. This is -12 times 3 is -36. Ooh, we got the case where we got exactly 0. That's that repeated solution. So we got one real solution. And graphically, again, that's where like the vertex is right on the x-axis. It's the only way for it to touch just once. Okay, and if we try this last one over here, try this one out, see what you get. Unpause the video when you're ready. All right, here's our work. Hopefully you came up with the discriminant value of 76. Because it's positive, that means we get two real solutions. My graph will cross the x-axis twice. And I know that just from finding the discriminant. So a quick way of telling some stuff by looking at the equation without having to graph the whole thing. You don't even have to find the vertex, which is kind of cool.